Hi, everyone. Welcome back to another workshop in the Commit to Change AI Agent Hackathon. Today, we have agent optimization with Opik. So I'm going to invite our speaker up to join me on stage. Vincent, you should be getting an invite, and you should be joining me up on stage now. Hello, Vincent. Thank you for joining us. You are muted.
Just give me 2 seconds. I just got to sort out my video.
No problem. We can wait. In the meantime, everyone, drop a message in chat for where you're calling in from. Hopefully, reasonable times for most of you. It'd be good to see how many people are making it to all the workshops in the series. 1 a.m. Oh my gosh, another one. I still love the dedication. Is anyone here at a normal time in their day? From London, Dan, you're in London with me, so it's a normal time for us. Some 9 a.m.s. Interesting. Okay, so only a couple of people up late for the session. Thank you all for joining us. We really appreciate the time that you take to attend these sessions live. We think it gives you a great opportunity to ask questions of our speakers and really engage in the hackathon. We will be putting out a post very soon asking you to share why it is that you're participating in the hackathon, and we'd love to see you posting about your participation and sharing a bit about your developer journey, what stage you're at now, what you're hoping to achieve, whilst the apps that you're building are designed to help people fulfill their goals for the new year. We hope that participating in the hackathon also fulfills a goal of your own to do with related to your kind of development career, depending on what stage you're at, whether you're a student, whether you've been working in the industry for 10, 15 years. It'd be great once we do put that out. I'll share it in Discord. It'd be great to hear some of your stories about why it is that you came across the Commit to Change Hackathon and why it is you decided to dedicate your January and some of your February to it. Vincent, can you let us know when you're ready to get going? Oh, I see you.
Yeah, you should be able to hear me now.
Yeah, can hear you. We can see you. Looking good.
Perfect.
We can hand straight over and get started with agent optimization if you're ready.
I just need another minute super quickly. It's just the Zoom didn't connect at the start. Sorry. So I've got multiple monitors, and if I don't set up the screen share, it all goes a little haywire for me here.
Nope, that's absolutely fine. In the meantime, any questions related to hackathon logistics? I know we've been answering lots and lots on the Discord, but if you do have any pending questions, now is a good time to ask. I'm here. We've also got some of the Comet team in the chat who can also help you out. So unrelated, of course, to what we're going to cover in the session, but anything logistics based, if you have questions, you can ask now.
I'm ready to get started. I'll start my screen share in a minute.
Okay, yep, when you're ready.
Custom slideshow. Swap the displays. Cool. I'll just jump onto Zoom. Okay, so welcome everyone. Thanks for joining this workshop. Couple minutes late, but usually I give everyone a few minutes before we get started anyway. And I believe you're going to be recording this session as well, right, Rebecca? So you can share it with people that can't join. Amazing. So I'll be flicking between a couple of screens as we go. This will be more like a hands-on sort of interactive workshop, but I'm going to spend a couple of minutes to just kind of talk through a little bit of theory at the start of this session. I think it's really important to sort of cover some of the conceptual aspects of this. Otherwise, we end up jumping into some of these like really technical conversations, and it's a good idea to sort of ground everyone into the same concepts as much as possible. Into my screen. 2 seconds. I'm not having a good day with my computer. Sorry. This is the right one. Let's try this again. Cool. So hopefully you can see my screen. A little bit about myself. I do work at Comet, as Rebecca has mentioned, but I've been in the industry for the last 2 years, 20 years. I've worked everything from like software engineering all the way to data analytics, data science to AI engineering as well. I look after developer relations, but also do AI research over at Comet. Apart from all these nice logos and everything you do, you'll see on the right, there's like a picture of me using Oculus Rift. This is in London. I grew up in London. And this was like, I don't know, like 16 years ago. That was a very first version. And when I put it on, it had like a warning sign, don't use for more than a minute, it's a test version. And when I put it on, I started like using it for hours on end. And then when I took it off, my vision turned into like this B vision. I started profusely like kind of vomiting. The story with this is that like I love to test things that are new. I love to kind of experiment with new ideas and new concepts. And usually when you're working on anything on the edge, on the bleeding edge, usually it's kind of like a janky experience. It's not always the best. So it's nice to see people sort of like partaking in this hackathon, like experimenting with new ideas and new techniques. And the concepts I'm going to talk about around like sort of this world of like automatic prompt optimization and agent optimization is a very sort of newish experience, not something that like a lot of people are sort of somewhat new to. So it might feel like a weird experience, but just bear with me as we sort of go through it. So we built this SDK called like the Agent Optimization SDK. And essentially it's this open source SDK that allows you to run like these various optimization algorithms. And I'll walk through like some of a little bit about like how these algorithms actually work and how they come together. But the promise here is really that you can use the best optimization method. You can take your various chat prompt or chat prompts within your agent architecture. And the idea is that like AI can potentially help us optimize our uh, particular agents for us. I think we're at a point now where people smashing words into a keyboard, what I would call uh, doom wordsmithing and just trial and error stuffing words into a prompt and expecting that to magically work. Uh, I don't think that kind of works in 2026 anymore. I think we need a bit more like a methodical process to help us sort of get to that. And apologies for some of you that may have seen these slides in the past. I know some of you joining may have seen some of my content before. So what I am going to talk about is this sort of concept of like this impossible triangle. It essentially boils down to a set of basic needs, right? So when we make a choice around how we want to optimize our agents or how we want to build an AI agent or how we want to do anything, it really like this concept or this like balance between speed, accuracy, and cost. We can have an agent that works really fast and really accurate, but the cost is going to be really high. And this is like a kind of constraints of like AI agents today. Like I think, you know, just like the common problems we have with like architectures and frameworks and systems, we know that this is going to be a sort of challenging space. So it's when we kind of think about evals and when we think about how we optimize things, I think it's just good to bear this in mind around sort of your choices. And yes, there's design architecture changes you can make. So you can put like one agent in front of a customer or a user that's fast and it's accurate. And maybe that talks to like the more slow running agents in the back that's slower, but has the accuracy that you need or is cheaper to run. So there's different sort of aspects of that you can sort of design. But for today's exercise, really we want to sort of think about evals as like this concept of like speed, cost, and accuracy. So as we started with like prompt engineering in 2022. For those of you that really kind of jumped into this stuff early, to 2023. And then we had this aha moment of sort of context engineering. And I'll put that into the likes of like RAG and everything like that. but I'm kind of coining this term that we're moving into in 2026, this sort of world of like intent engineering. And what that starts to boil down to is, as I mentioned in prompt engineering, we had this sort of troubled world of like trial and error, gut feel, the cycle of doom wordsmithing, which was sort of somewhat getting us there. But really, it was like, just let's shove words into an LLM and see what happens. Then we had this sort of inception of context engineering, where we can start to steer agents with some form of intelligent data retrieval, right? So this is like, can we bring the world of search engines into our agents with things like RAG, long context windows? I'm even going to put MCP servers and clients into that space, where essentially we're giving agents tools to be able to fetch the information that they need. And this is about making the memory a little bit more efficient. But there's still an issue where we're essentially creating these experiences from from the wrong lens. It's still very much like, I'm building this one generic agent and I'm trying to trickle that down and hopefully get to an experience that my end user may like. But what if we had this sort of new concept where we flipped it on its head and said, hey, we knew what the user wanted as the output, and we started that as a space at the building block, and we sort of work backwards from there. So to kind of give you an idea of what that looks like conceptually, I'm building, let's say, an AI therapy bot. Instead of trying to build like the right tools and engineering and all the fancy sort of system prompt, what happens if I had a data set which had examples of the types of conversations that I wanted my agent to have? And then I built my agent based on those example conversations. So I started with the output and sort of worked my way backwards. The idea is that if it got really close to that, then I built something that meets the needs of the end user. Whereas the other way around is like, we built something and we're trying to make it as close to what the end user wants. And that's kind of like a shift, so to speak, in the way we sort of think about this process. Whoa, jumped. Sorry. Don't know what's happened there. Ooh. Okay. This one's new for me. Bear with me. Nothing sensitive on the screen, luckily. When you work in open source, everything you work is in the open, so it's all good. So let's go again. So when we think about our agents, we have our prompts, we have our tools. The tools can be the MCP servers, and we have some sort of input that comes in, and the input could be the data set, it could be your question. But in essence, when we do prompt engineering today, it's like, hey, we look at the system prompt, we take that out, we go, why is this model hallucinating? Why is it making a mistake? We build a new prompt, we stick it in, we go through this cycle. And this is essentially prompt engineering now. But it's flawed for multiple reasons, because we're missing that signal. We don't have an idea of like, against the user's expectations, is it meeting the speed, the accuracy, the cost? Is it sort of the end user experience that we were hoping for? And when we start to do anything sort of semi-automated, it starts to look a little bit like this. So if we put some sort of testing process in place, an eval in place with some data set or some sort of automation, and we had our metric defined, which could be hallucination, a specific cost, or talk to a customer in a certain amount of time with a loop with a data set, this is essentially a more sort of automated aspect, but it gives you confidence. So this is what evals looks like today. So when we use like something like Comet or another tool or another framework where you're automatically testing your agent with a data set, we're kind of taking away that gut feel, and we're sort of automating this process and giving you better strength around sort of how this works. But as I mentioned, it's somewhat flawed for a couple of reasons. So that's kind of step one. That gives us an idea of sort of like, prompt optimization. We have some level of automation, but we're not really solving anything in a sort of automated way. So the question then becomes, what if we could automate this process entirely? What if we had LLMs do the prompt changing for us? Well, the short answer is yes, we can. We started in 2022 with research and still ongoing research. The meta prompting in Jan 2024 was sort of this sort of aha moment where it was like we can prompt these LLMs in a very specific way using chain of thought reasoning, and it will help us write better prompts, or it will help us write better instructions and do tasks a lot better. So we could take this concept and we can get it to write better prompts for us. So yeah, we can use LLMs to optimize these instructions. So when we talked about the meta prompting process, it essentially became this concept where we have this like what we call a meta reasoner. And this meta reasoner is essentially an LLM with a prompt, which if I have time, I can show you all. I'll send the link around. And it goes, hey, you're the best AI prompt engineer. I'm going to give you some prompt. Here's some idea about some of the stuff. And here's some examples. Can you build me a better prompt that solves this? And essentially each time we run this meta reasoner, we might create, say, 6 prompts. We test it against that metric we defined. We go back, we loop through it, and the idea is we find a better prompt. So in the case of my example, when I gave this presentation before, I was talking a lot like ramen. So the example, the analogies I came with, like, hey, the chef looks at the recipe and says, can I write a better one? And just keeps rewriting the recipe until someone likes the food. It's still very brute force, but surprisingly, because we can do this in an LLM and run it in the background for ages, it surprisingly works. Not to the best examples that we can imagine, but it somewhat gets us there. I'm going to run through these slides pretty quickly, by the way, everyone. So we will share this, and I'll try and get the slides sent out as well, because I do want to jump onto the code. But I think the theory is also quite interesting as well. But there's more alternatives than just share provost. Yeah. So the example I gave here is like, hey, you're going to pick ramen, so you just buy all the ramen in the ramen shop, and you hope someone likes them. You don't know which flavor they go for. If you do like ramen and you have a particular one, you're like, put it in the comment, because I will read through it later. I think it'll be quite interesting. And if you don't, you should start liking ramen. But there's more alternatives other than sort of brute force as well. And we had this like new wave of optimizers sort of appearing. So we have these genetic algorithms, which I'm going to touch on super quickly. And we have this concept using like what I would call like retrospection or reflective sort of optimizers. Genetic algorithms essentially work in this way, where on the left is the meta prompter. We have a given prompt. This was our starting point prompt. We created initial prompt, and then we said, hey, give us a number of examples. So it gave us a number of examples, and we found that this prompt over here was better. So then we ran the meta prompter again, and it gave us a number of examples, and that was the one that was better. So each trial we went with, we found a better prompt. But it's kind of like selecting the best one. In a genetic algorithm aspect, which there's things like GEPA, which is another sort of optimizer. We have our own similar evolutionary one as well, is that when we go through this optimization process, we have like these, let's call them children for the better word, that start from this initial parent prompt that we started with. So we come up with different ways to make variations of these children, which we call mutations. Same as how genes would mutate in the wild, we might randomly remove words from the prompt. We might swap things out. We might change the order of the prompt. Now, some of this stuff might look like total nonsense, but what ends up happening is some of these mutations, or the same as in genes, will lead to a better outcome. And essentially what we're doing here is we're finding the combination of the parents that would give us the better genes, that would give us the better prompt. There are some other methods that are used here to avoid overfitting. We tend to also remove the top 5% and the bottom 5% of the gene pool. And every so often we would introduce new genes by reintroducing the initial starting prompt, or getting the LLM to create a new prompt based on some examples and feeding that back into the population to avoid the population from kind of converging too much and having the same genes so to work with. So the genes in this case would be the parts of the prompt or the words inside the prompt. And we felt that this aspect was like the sort of the late stages of 2025, about 6 months ago, really started when the rubber started to hit the road, and we started to see some like really promising results, where I strongly believe it's actually past the point of, in some cases, writing prompts better than a human can, because it's able to find quirks inside of that particular model and the way the model behaves against the metric that you've sort of defined. So here we have a population of prompts. We create children, we mutate and merge those components of those prompts together. We evaluate them. There's this concept of a hall of fame where essentially we know which parts of the genes of the prompts themselves essentially are good. So we keep sort of like a register, like a census in this case. I might go for census, actually. I might change that. It's a bit of wording. And then we kind of reintroduce that. So we keep going through this process until we hit a maximum count of how many times we want to run this, or we're happy with the results. So in this case, it's the same. If I use the chef analogy, multiple chefs are competing. The best dish wins and evolves. Losers go home. So if you've ever watched any cooking programs like MasterChef or Hell's Kitchen and things like that, that's essentially what we're doing here. Instead of getting one person to like keep hammering this home, we're creating these multiple chefs and we're kind of competing them against each other. And we're trying to like essentially breed the best prompt out of this aspect. And then the last one I wanted to sort of touch on was this hierarchical optimizers, which is the one that we're going to be running today in our workshop example. And the way to think of this is more as like if you're like an engineer and you're looking at a problem, you've already got a prompt or you've already got a system that you've built. You run something and you're like, well, I'm going to hypothesize that based on what I'm observing, I think that these 5 things could be going on. And the way to test these 5 things I think are going on is I can toggle these things or put some debug logs in or whatever. So in this example, the optimizer works by essentially running the set prompt through, looking at what's happened, observing the results. So this optimizer is a little bit more like a detective around the metrics. So it understands the metric a lot better. We have to provide it an explanation of what the metric is that we're using to score the optimizer with. And it comes up with these hypotheses. It reflects, it does like a retrospection internally. It comes up with some strategies on how to do it. It creates multiple prompts out of those strategies, tests them, evaluates them, and it goes through a loop. We find that this kind of takes this like very bottoms up approach, where the other one's taking a tops down approach. They kind of hit things a bit differently. In some problem spaces, we find that this works a little better. It's more nuanced because, like, hey, in the dish analogy, it's kind of like, oh, is it too salty or the texture's off? Let's tweak this, let's tweak that. So it's kind of getting us that like last mile, and it's clustering failures together to try and find a better prompt for us. So in the example that we're going to work through, this is the optimizer we're going to use. But because it's within the SDK, at any point we can easily switch between optimizers quite easily. Like we're not stuck to one or the other. You're welcome to test either one of these. What I would say though is that the more complex optimizers take more rounds to run. They are more LLM intensive. Therefore, you will need to spend a little bit more of like your tokens and API credits to make it work. Whereas if you were using like a meta prompter and maybe just like a Gemini API, in just a couple of trials, you might have like an initial half decent sort of prompt to sort of work with as well. Cool. So I'm just going to check the questions, and then after that, I will jump into the example.
The questions at the moment are mostly logistics related, so I think you're all good from your end on the content.
That's all right. Any questions from anyone before I continue on some of the theory, if like any of this didn't make sense or anyone had any follow-up? Because it'll make a lot more sense if we get some of the theory out the way and we jump into the example.
Give people a second to see.
Kind of confused what's going on.
Maina just joined, so I wouldn't
no, that's
worry
all good.
too much about that.
Sam, what's your favorite optimizer? Hey, Sam, nice to see you here. What's inspired the shift from genetic to hierarchical? So a couple of things here. I don't really have a favorite optimizer per se. Some of these optimizer algorithms I worked on myself as well. The the thinking behind them shifts as we try and find that next edge of like, how can we get it that next mile? If anyone's following the results around ArcAGI, which is like a puzzle, we're trying to get machines to play like these puzzles. Let's see if I can open up my browser. Just bear with me. And I'll share my screen. We have plenty of time for. How long was this workshop?
We've got an hour, so we've got 35, 35 more minutes.
Cool. I'll be super quick.
I think there's also a couple of questions in the Q&A tab, but Mattis has moved their question over to the chat, so there's only one.
Yeah, so there's these like ArcAGI puzzles, if anyone has seen them. Let me see if I can find the puzzles. Yeah, so like there's these huge puzzles that, I mean, depends. Supposedly humans can solve all of these, but some of them are pretty challenging. But when you look at them, they're like kind of logic puzzles. It looks like something you would have to do in like some sort of really complicated sort of IQ test. And these are puzzles that are used to sort of like to see if models are quote unquote closer to intelligence. I'm not going to say they are intelligent, but sort of closer to intelligence. And what we're finding is that like, you know, there's some recent results that were published on solving these puzzles, which kind of solves this puzzle entirely using existing LLMs. And that was using the hierarchical method, using the reflective method that I demonstrated, which takes like a GPT-5 from like a score of 55 to like 90, for an example, on this puzzle benchmark. So we're finding as we're trying to solve problems with LLMs and the LLMs get smarter, we're finding more interesting ways to build optimizers, so to speak. So hopefully that gives you a little bit of context. I'm just going through the questions now. Can you expand on genetic modifications, Mattis? The genetic modifications, some of them could be things like, I'm going to swap the order of the words in a sentence in a prompt. I'm going to make cinnamon, so I'm going to rewrite sections of the prompt. I'm going to change the order. I'm going to remove entire sentences from a prompt. So there's some like really simple sort of modifications that we could essentially do. David, how is the best prompt decided? So that's a really good question. The best prompt is decided based on the, oh, that's really weird. When I start sharing my screen, I can't move my mouse around. The best prompt is decided when we define that metric. So in the example I'm going to walk through, we will have a metric that we will define based on some form of accuracy that we're looking at. And that's essentially what we would use to solve this. Cool. All right, I'm going to jump into this example. And is my mouse working? Yeah. My computer is doing strange things today. So I'll put the example that we're going to walk through into the chat. Oh, I'll put it to everyone. And I'll proceed by sharing my screen. This is, okay. So I'm just going to change my, for some reason, my screen setup has gone a little haywire. That's why that little notch. Okay, so the example we're going to work through is something I published really recently, but because it's written up in a nice explainer, makes it easy for everyone here. So if you did ever want to sort of walk through it and get the explanation, we can. We're not going to talk about what we're optimizing. I've given you sort of like what optimizers are. I've given you sort of an overview. But this is an example we're going to use, which is an agent that has multimodality involved. So the use case is I'm a car driving on the road and I have a camera attached to this car and it's taking photos of the road. And what I wanted to do is detect hazards and maybe provide a signal to like the self-driving car or to the user to say, hey, by the way, there's like a cat on the road, stop immediately. Now, we need a data set to work with, which I'll walk through in a little bit as an example. But really the idea is, can we go from this sort of highly complex, really simple prompt here on the left, which gave us an initial accuracy of 15%, and I'll talk to how we calculate the accuracy, to this sort of optimized system prompt with an accuracy of, say, 40%. Now, we are using a low sample, so we are using a low number of data set examples. So you are going to see some like really wild swings. It's going to overfit, but similar to training a model, if we run it for longer on a larger period of data, we should be able to get some interesting things out here. So I'm not going to talk through what we're doing in optimizing, but I will start to talk through sort of like how we would sort of build this out. So I'm going to kill this side panel, push this to the right. So in our case, normally you would ensure that you are on essentially a latest version of Python. I think the optimizer uses, I think we only support 3.11 from memory. 3.14. So yeah, 3.10 or above is recommended. So I think I'm on 3.12. So this is Python only at this stage. We may or may not have a TypeScript version of this optimizer. If you have interest, do let us know. And we are working on a UI-based no-code version of this sort of optimization process as well. But if you did want to get started, you could follow sort of the Python example. In this case, I've already installed this in my environment and essentially run this Opik configure. So if you're using Opik for the first time, you have to use Opik configure, and essentially allows you to hook it up to your cloud environment. So if I go to comment.com, you'll see that I have my UI. Now you're gonna ask like, why do I need this Opik component? I could just run this SDK on its own. Now, when we run the evaluation process or when we're recording our optimizations, that gets stored up onto the cloud here. So if I show you an example of something I did, like a self-driving car one, maybe something I ran for a little longer, it'll look a little bit like this. So we'll be able to see the prompt, we'll be able to see the data going in and out. If you're running this for like 20 minutes, half an hour, it records all your results so you can grab everything. So everything is all managed in here. The existing data sets that we're using, it all gets managed in here as well. So using it from here makes that process a little bit more sort of easier. We will need an API key. In my case, I'm using OpenAI, but you could also use a Gemini key and swap out the model for, say, a Gemini model. So nothing is stopping you there. You can also run local models. So you could use Ollama if you wanted to, and you could wire that up. If you need some examples on sort of how to get to that, if you write Opik Optimizer docs, in our docs, you'll see on the top right-hand side, we have documentation, but we have agent optimization. And here there's a section called configuring LLM providers. So you'll be able to see some examples of if you wanted to use Ollama or something else, we have examples on like how to configure that as well. So the example data set that I want to use is something that already exists. It's a research data set called DHPR, which I'll jump into and show you all. But the main thing to sort of work out is that if we wanted to run any of this sort of optimization process, same as you would be training a model, you will need a data set of some description. Like we can't just blindly and go, hey, I want to just magically optimize my model without any data set. I need a starting point. I need to be able to tell the machine like what good and bad sort of looks like. So this data set is 1,000 rows of validation, 1,000 tests, 13,000 trained. I think we're only going to use like a sample of like 50, and it looks like this. It's like dash cam videos of cars on the road. This one's a good example. There's a person on the road there. So if I scroll across this one here, you'll have things like, we're too close to a stop sign, or we're driving too fast for the parking lot, or, things like that. So these hazards have all been sort of identified. There's a speed on there, and there's bounding boxes. I'm not going to do anything with the bounding boxes, but that would have like the hazard sort of highlighted. We could potentially do something with that in this example. So this data set is just dashcam videos and human written annotated hazards. So idea is that, like, can we feed an agent these images and some examples of these hazards written in human language, and get the agent to a point where it can actually write the same sort of text just by feeding the images in? Like, that would be pretty cool, right? So then this is this concept that I'm speaking of, like, hey, we start with the example, and using that example, could we, in theory, sort of create that? So could we create that same output as well? So let's start with example. In my project, I'm going to create an example.py. I'm going to do edit example. I will switch to a proper code editor. What is going on? Try cursor, might be easier. I've already got it open on the side. Here we go. Example. So this example we're doing from Opik Optimizer datasets, import driving hazards. The data set equals driving hazard, and the validation set equals driving hazard. So with this particular example, we need to start by importing the data set. You'll notice that the data set already exists. So in the SDK, there's a number of data sets that already exist out of the box. You can also bring your own data set. So the data set equals just needs to return like an Opik data set. I'm happy to sort of give examples of that, what that looks like as well, for those of you that want to sort of run your own data sets through. But Cursor and some of these coding IDs should be able to do a lot of the heavy lifting for you. Since the data set's already built in and it will run it, we want to create the two data sets. In this case, I'm going to create one, which is, using a count of 20. So just don't use the full data set. You can see Cursor's given me a suggestion to use the testing split. So we'll do that. And that's going to be count 5. So I'm going to just save that. I will not use that as my IDE. So we'll do Python example. So when I run this, in theory, what it should do, it should create the data set for us. So it should go to Hugging Face, download the data set. It's finished executing. So if I jump into Comet, it's called hazard. You can see we've got our test 5 and our train 20. So if we click on our test 5, it's got these examples in here. We can see the images. We can work with that. The great part is if I was just doing some basic sort of, if I was doing some sort of basic example, I could also do this in the UI. So I could say, here, collect the data set. What was it called again? So test 5. I don't have an evaluation metric set up in here, but I can say, identify the hazards in the image. So if I didn't want to run like this whole entire process, I could test it in here. I can see, okay, is this actually working? Okay, could read the image. You can see it's using the image. I can easily attach another image if there was multiple images. So our playground supports this multimodality. We can read from the data set, we can tune the prompt, and we can test the prompt. Or we could define this as a metric. So we can create like an LLM as a judge metric, and we can run that. And that allows us to kind of test this prompt and see how it's behaving and see. But like, this is going to take me a while to try and write this prompt. And I can probably eyeball it looking at the examples to try and do it. But essentially this makes sure that, everything is sort of running as we would sort of expect it. You'll also notice there's a validation data set when we pull this data set together. So when we do the validation data set, the optimizer will know to then rerun this test again on the validation data set to make sure its changes are valid, as you would expect. So one of the human examples looks like this. Entity 1 breaks his car in front of entity 2. I've shown you an example. The metric we're going to use in this case, we can use another LLM as a judge. We can say, look at the image, how correct is this answer, things like that. But the reward mechanism that we're going to use as the metric is a simple sort of text-based comparison. So Levenstein distance ratio essentially works by comparing A text to B text by comparing the distance and the volume of changes. So as you can see on this right-hand side one, even with 2 words, minor edits, the ratio has shifted because of the number of characters essentially that's changed. And that's given us a match of like 98%. The reason why I'm using this, it's fast, it's quick. It may not be the most reliable because it's not looking at like how similar the words are. It's literally looking at the text from a math perspective and going, hey, this number of characters have shifted and changed. So the idea is that we're going to tell the optimizer that as it creates new prompts for each data set and evaluates them, how close are the examples that the LLM is generating for each one of these data sets to the example we have in our data set. So we're going to get like a match rate percentage, and we're going to keep recycling through that at speed, and hopefully the optimizer should start to make a gradual sort of improvement in that case. So then we need to sort of define our metric. So if we go back to my cursor example, let's turn off this sidebar. We've got our data set, and the metric definition is done by importing our inbuilt metrics. So we have things like Levenstein ratio and LLM as a judge metrics in there. And if you remember earlier, I did mention that the reflective optimizer needs a way to understand what the metric is so that it can do its reflection process. So here we define the metric. We're mapping the hazard column as the initial reference point. So this is where it had the human annotation in the data set to the output that's coming from the LLM. So we're comparing the LLM's output to the hazard that's in the data set. And we're also returning this score result. So this has the value and the metric name, but also needs to include an explanation of what this score is. This is only explicitly used for the reflective optimizer. We are working on some improvements where you don't have to do this extra step and it's done for you. But in the meantime, you do have to define it. So what happens is when it goes through the reflective process, it knows what sort of the sort of optimization looks like. And I'm going to give it the starting prompt. So if we go here, let's give it this chat prompt, put it to the top. And this is our system prompt. So you're an expert driving assistant. So this is me attempting to write the initial starting prompt that I want to work with. And we just essentially pass it through in this sort of OpenAI chat message format. You'll see we have the text, which is the system prompt. And in the user prompt, we're just going to pass in the image from the data set along with the question. So if you remember in the data set, there's a question, and the question is based on my dashcam image. What is the potential hazards? So same question that was asked to a human, we're going to ask the LLM, and we're also going to pass through this image that's in our data set. So anything you see in the squiggly lines is just mapped. The brackets is just mapped. Speed this up. We don't need to go through that. And now the fun stuff happens because now we need to import the actual optimizer itself. So here, I'm going to import that in. I'm just using GPT 5.2. Why is it giving me now? Need to fix that later. And this execution. So a couple of things that are happening here. We have our optimizer and we have our optimized prompt. So what's happening in the optimizer aspect is that we're essentially defining the optimizer and we're giving it the configuration we need for that. So you can see we can give it the model that we want to use, the model parameters. In this case, I'm setting the temperature, but this could be like a Gemini, it could be an Olama. And then the result, the part that's actually going to run, we map in the prompt, we map in the data sets, we map in the metric for some reason. It's up here. Yep. The number of trials, so how many times we want to run this. I'm going to reduce this for argument's sake, make it run 5 loops, 5 iterations. And then the response that we get from here, we just run a display function. So this will make sure that the results that we get at the end work. And as with all of these, fingers crossed the demo gods this works. Because last time I did this, it didn't go in my favor. I need any. Switch branches for a second. Oh, annoying. This is a specific version that I have on my machine that's problematic. Should be working fine. So here we can start to see that it's picked up on it. Ignore the pedantic errors. It's still working as normal in the background, and it will start to write the evaluations. You can see the score. This is just a developer version I have on my machine, so there are some errors. I had to switch between versions just because of that package version mismatch. You can see the scores come up to 17%. And if I go into my comment browser here, into the optimization studio, you can see that it started to run here. So it's going from an initial score of 17% on the first run. It's already made its slight improvement, and you'll start to see it will make some, it'll start checking the different failures and start iterating on itself. I'll leave that running in the background, but it tends to look a little bit like this. So here we go. So the failure modes include things like the checklist versus collisions. It's missing entity n equals. So it's already looking at the data set, understanding what's wrong with it, and making gradual improvements to the examples by sort of comparing it. And it's making data set specific sort of adjustments and improvements, as you can see. So here, just based on those improvements and the root cause analysis, it makes a new set of prompts, tests those improvements, and you can see we've jumped from 17% to 35%. And it will just keep going through this cycle and keep improving the prompt. And if I go into the dashboard, I should start to see that new 35% prompt is here. So I can already see that the prompt is quite different, where it's starting to give like specific examples of what to do and what not to do. And we've been able to run this sort of example in only just a couple of trials. So in terms of LLM calls, maybe 10 or 15 LLM calls, and we've got like a maybe 2-3x improvement on our initial prompt. And as you can see, it will continue to do this sort of gradual sort of improvement. So I mean, that's fundamentally it. The sort of the key things to point out is you do need a data set to sort of work with. So you can import a data set. We have the ability to kind of synthetically create data sets as well. There's some example repos that I have. There's also the potential that you could take something that's running in here, pull out some of these examples, as you can see, and add them to either like an annotation queue or add them directly to a data set. So you can use potentially existing examples that you have as a data set and sort of build on that as well. So you would need a data set, you would need like a definition of a metric, and you would need to sort of like run that through a couple times. The only other piece of thing that we do get asked a lot is if you go through the docs, there's a lot of examples. We also have like more complex metrics, so like multi-metric, like where you want to combine 50-50 metric, or you want to include that cost accuracy stuff that I was speaking about before. So like the LLM cost or the time it took to run the prompt as part of the metric definition as well. Cool. I'm gonna pause for a second and go through the questions.
We've got most have been kept to the Q&A tab, so that's probably the best place
Okay,
to
I'll
look.
switch. It's hard when you've got like multiple screens and you're like trying to
work out where the pop-up is opened.
What is HAPO? HRPO is the Hierarchical Reflective Optimizer. So at the start, I walk through like 3 different variations. I walk through the meta prompting sort of optimizer. So if you go to our optimization algorithms on the left, I spoke about the meta prompting. I spoke about the evolutionary ones, which is both GEPA and our evolutionary optimizer. And I spoke about the reflective one, which is HRPO. There's also few-shot Bayesian. Few-shot takes examples from your data set and finds the best combination of examples and order and number of examples to put inside of your prompt. So these will come up as part of your chat prompt as examples. And based on some requests, there's also parameter optimizers. So this would tune like the top P, top K, temperature, things like that as well. You can chain these together. So you can go, hey, I want to run the hierarchical optimizer, gets me to like 60%. Then I want to include some examples from the data set. And then lastly, I want to just touch up on the temperature parameter to make sure it always gets the right answers for me as well. Can you expand on the genetic modification? I've done that. With LLMs being non-deterministic, this is a question. What is the strategy of identifying which parts of prompts to keep and induce for better evaluation? So I don't know if you saw my presentation. I'm just going to click out of my presentation for a second. This genetic process is one method of potentially guiding the LLM and finding issues that we feel could be problematic. So those parts that they get edited. So in the case of GEPA, it breaks this huge prompt into sections and small pieces, and then kind of works on optimizing those small pieces and working out which small pieces work well. Or in the case of the reflective optimizer, we're looking at strategies and running hypotheses and understanding what works based on a hypothesis that we maintain. So there's different ways. There's more sophisticated methods where we could potentially look at the weights of the model and use things like mechanistic interpretability. But at this moment, I think the beauty of using something like this is that you don't need to touch the weights of the model. You're just changing the system prompt. So you can take an existing model, you can take a frontier model like a Gemini, and you could tune it to your use case and to get the most outcome out of it. And we find that like the cost benefit is that you're able to get a lot more out of these models without having to do the expensive fine-tuning process or go through the extra mile. There might be use cases where that is deemed as necessary as well. Do you use linear programming for evaluation of LLMs? In which case, of a positive answer, in which way? I don't do linear programming, so I don't know how to answer that question. Apologies, but I can look up and get back to you. Santiago said, from what you've seen, what do teams most often get wrong when they try to optimize an agent? Are they measuring the wrong things, testing the weak eval data? Yeah, so when we think about optimizing an agent, I think just looking at failures and defining a metric of success at the start of building what your thing is trying to do. So starting with like mocking the data set, mocking the examples if it's a chat, What does those examples look like? And before you even run the optimization, you can probably get away with just building a small prototype yourself and just seeing how it behaves and writing just LLM judge evals to say, okay, how much of this example matches my expectation? Like a lot of this can be done without having to resort to prompt engineering and just good hygiene. But at the same time, it's good to sort of do this as well. Very good question from an anonymous person. Can Opik support audio input in the dataset? Please raise a support ticket because I worked on a lot of these multimodal features and audio should be supported. You do have to base 64 encode any images, audio, video. We have video working as well, by the way. We have some video optimization, but it's very, 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 very token heavy. So do sort of keep that in mind. So to the person who's anonymous, if you want to drop in the Discord or the Slack and just tag myself if you can find me. If not, just put in the channel and I'll just keep an eye out and I'll see if I can help with the audio example as well. Heba said, is prompt optimization safe to do in production with minimum supervision? For example, when a refine a conversational agent to use the same style as a user, but we need to first collect a sample of their way of writing to then pass into the conversational analyzer agent. So as I mentioned, there's a couple of components to this, right? So you can capture the traces of your actual live use cases. And based on those traces, you can also then create a data set, or even better, create an annotation queue and have people in your team annotate these data sets and then turn that into a new data set that's been completely annotated with good and bad examples, build a metric and run it. But the same thing goes, like if you're saying, is prompt optimization safe? Is the same thing I would question, is any prompt change safe? How do you test your existing prompts in your production environment? So that's something to sort of think about here as well. I'm going to keep going through the questions. Someone said my training data set is 78,000 rows. What is Opik's data set limit? We work with large enterprises, and I don't think I've faced this question before. So my assumption is a 78,000 row data set should be fine, Corinne. So if you have any issues with data set limits or you reach any sort of limit, it will probably be rate limiting on upload. There are some batch API endpoints for like uploading large files. The front end may not let you upload that, but you can use the SDK directly to facilitate your upload. So if you have any issues with large scale data sets, yeah, do raise a ticket, but that should work fine. There was a question about where the code is. So if you go to GitHub and you go to Opik, Comet uses a mono repo architecture for Opik. So if you hit into SDKs and you go into the Opik Optimizer, you'll notice that the entire optimization SDK is open source, which also includes the optimizers themselves. So if I click into the SRC optimizers, click on algorithms, click on the meta prompter, click on prompts, you'll see that these are the prompts that it's using under the covers. So you'll be able to see all these examples. A lot of this stuff is open source. No, if not all of it's open source, sorry. So this is all available, and this is what we build the packages off and publish to PyPy. So the code is publicly available for anyone who wishes. If you go into scripts, it's gone. And then you go to multimodal example. The example I've just walked through is also available here for you. So I will drop that into the chat. I'm happy to run over and just quickly answer these questions. So I'll click, do you recommend running performant models for the prompt optimizer, or light models would work well? Yeah, so there is the option to pass in a parameter. If you go to our API, we go to optimize prompt. Not all the optimizers support this. We have another version coming out. where I think it's the Gepper, the hierarchical one. One of these allows you to pass in a reasoning model. I think just a meta prompter now, but we are releasing a new version where all of them will support it. I can't find it, but you can pass in a reasoning model, which means that actually you use one model for evaluating and one model for writing the prompts. So you could run your model on a small model like a Gemini Flash, but you could do the reasoning and the prompt engineering work on like a Gemini, like Pro model, and that way it's using the brains of like a bigger model to write the prompts, but it's testing it on the smaller model, and that's a really good strategy in terms of getting more out of a smaller model as well. I've answered this question. How would this navigate or deal with non-native speakers who might interpret the new output as being systematically different than the original intent? I think when we're working around like multilingual use cases, it just comes back to your metric definition. So as long as you have a way of measuring good and bad, or your model that you're using understands that language, or there's a human in the loop process, it would work the same way as a prompt engineer would in this given scenario as well. Felipe said, once we ran an optimizer with the reflective optimizer at the end, should we run the resulting prompt into another optimizer, or do we start from scratch? There are some examples in the docs, chaining optimizers. So if you click here, I give some examples of how to chain these and what that might look like, and how you could sort of plug these together. So have a read through this, and hopefully this helps as well. Considering that we have a new project and we don't have test responses, what is the best practice to work with? So I think the best practice is to like mock data, even using an LLM, to create an example of what good looks like in your given scenario. So if it's a therapy chatbot, what does that conversation look like? You can mock these conversations, you can tune it, and that could be your starting point for your data set. And then Santiago, for your last question, if you click through on the overview, you'll see here there's some like what this is good for, examples across each data set, and then at the top of each one, we give a brief explanation and some of the things that they're good for. But I think it's worth kind of like experimenting with these to get a good idea. Cool. I think that covers everyone. It was very rapid, apologies. But I did want to cover some of the theory as well, and I will make sure that those links get set around along with the recording, potentially copies of the slides as well. So we'll try our best to sort of package that up and send it to everyone. If you have any more questions, do direct them to Slack and Discord. For those of you that are joining remotely and want a way to sort of raise any questions, you can kind of reach out to me directly, LinkedIn or X, or just respond to me on the Luma invite as well, and I'll be happy to reach out and help you all. Thank you so much, and thanks for joining.
Thank you so much, Vincent, for running this session and for speed running everyone's questions. I'm sure everyone really appreciates it. And thank you everyone for attending. We really appreciate your time and you coming to join us live. The recording will be available, and as Vincent said, we'll try to get you as many of the resources and links that have been put in the chat today onto the hackathon page so you can access them after the event ends. Otherwise, everyone, have a great rest of your day. Have a great rest of your night if it's 1 a.m. for you. And we will see you next week for our final workshop in the hackathon run by Google DeepMind. But in the meantime, everyone should be in the ideation stage. You should be getting ready to create your project and form your team and start building. So we'll end it there because we've gone over time, but we will see you all over in the Discord.